Uh, okay, so next part we're going to talk about chapter 3, which is a mole. Let me share the screen. Okay, so first we're going to talk about the concept. Okay. The concept mole. Okay, so I think most of you already know what is a mole. Okay, is there anyone can give me tell me what is a mole? Just a rough concept. What is a mole? Okay, so what is mole? No, mole is a number of something. That is true. Okay, mole is a number something. Mole is kind of just a number. Okay, mole is just a number, but this is a really, really big number. Okay, so mole kind of is a really big number. Is a really big number. Okay, this is really, really big number. Okay, so we know usually we talk about we have a one pair something. Okay, if we have one pair something, we know the pair is referred to time two, right? And we also talk about if it's a 1 dozen. Dozen, that means referred to time 12, right? So this is 1 dozen, okay? But one mole is just like a pair, dozen, and mole has a really, really big number. Okay, the mole, one mole is you need to time like a 6.02 times 10 to the 23. Okay, so this is a really big number. You see, time 10 to the 23. Okay, so if you cannot imagine how much it is, then I just give you an example. Okay, so you know the small candies, right? Small candies. Okay, the small candy one. So what do you think? Or lollipop? Okay, how much weight of those candy and just one candy and one lollipop? Pretty small, right? Just a little bit. Then what do you think? If we have a one more, if we have a one more of the lollipop, okay, if we have a one more of the lollipop, if we have a one more lollipop, what do you think? How much weight it is? That's gonna be very big. Then can you imagine how big it is? Is that big? If we have one more of the lollipop. Come on, think about it. If we have one more of the lollipop, what's the weight it could be? Okay, what's the maximum? Okay, wait, you can think about it. Give me some input. If we have one more of the lollipop, think about it. cruise ship or something. Okay, so well, actually, then I just let her know. Okay, one lollipop. Okay, Berthra, what do you think? If we have one more of the lollipop, how much it could be? How big it could be? Yes. I know it's really big. Yeah. So Colin, what do you think? Okay. How big it could be? One more of the lollipop. If we have one more of lollipop. Okay, James, he's talking about one more of lollipop could be a cruise ship, a cruiser. What do you think? Okay, how big it could be? Spaceship. Okay, did you see a spaceship? Well, I'm just talking about it's bigger than that. Okay, so it's about like a 1/10. 1/10 of what? 1/10 of the mass of 1/10 of the mass of Earth. Okay, so that's a really big number. So can you imagine that? It's a really big number. Okay, and one more example. Okay, so you see a donut, right? Donut probably like that much high. Okay, so this is a okay. So I draw a donut. This is probably a donut. So this is the height. The height is pretty small. It's about, what do you think? It's height like one, it's less than one inch, I think, right? So the height is less than 1 inch. If we have one more of donut, if you want to stack, if you want to stack one more of the donut together, what do you think? How long it could be? Okay, if you stack one more of the donut all together, of course it can't. We cannot do that. But how long it could be? How long it could be? Okay. What's the longest distance you can think about? One more donut. It's the distance to a moon. Okay, yeah, it's much more. It will be a bit under 9.5. Yeah, so that's distance. Okay, so it's from Earth to the sun and come back again. Okay, so that's really, really long. Okay, from Earth to the sun and come back. So this, you see, generally one more of the number, one more is a number, but this number is really big. You can't, I mean, it's really hard to imagine that. Okay, so for the mole, that's a mole. It's hard to imagine, but then you think about why we need to use the mole. Okay, the mole, generally this number is not suitable for our daily life. It's not suitable for our daily life. Okay, we cannot have like a one mole of the chair. Okay, or one mole of the table. That's too much. Okay, but when we talk about the small atoms, okay, or small compounds, so several elements combined together, we talk about the molecules. We can use mole because the molecule is really, really small. Okay, molecule is really, really small, and if you're talking about the 1 mole of the copper, okay, or 1 mole or something, 1 mole copper, probably the size is just like that. Okay, so it won't have too much. Okay, so that is why we use mole for the chemical compound. Okay, because the molecule and atom is very small, if we add a mole, that's perfect for us. Okay, and another good point for the mole, we use mole, is because, okay, let me switch. Can anybody look at this periodic table? See the periodic table? Okay. So when you look at the periodic table, okay, last time we talk about atomic mass, right? Average atomic mass, AMU, and I shows the AMU shows the number shows here, like a boron elements has a 10.81. That is 10.81 AMU. This is the average atomic mass for the boron, but this is also the molar mass of the boron, which means molar mass is talking about 1 mole of the boron is equal to 10.81 gram. Okay, 1 mole of the boron is equal to 10.81 gram. So 1 mole of the carbon atoms is equal to 12.011. Okay, so I just assume this is 12. Okay, 12.0011 gram. Okay, so if you look at the small numbers here, you will know how much weight it is for 1 mole of those atoms. 1 mole of these atoms. Okay, so here it gave us good things. Okay, so in the periodic table we can find the molar mass. It's called the molar mass in periodic table. Okay, molar mass, just like you can see 1 carbon, it shows 12.011 gram. Okay, we talk about molar mass here, we talk about as a gram per mole. Okay, gram per mole, because this is molar mass is 1 mole, we have a 12.011 gram. Okay, 1 mole, that means 1 mole of carbon equal 12.011 gram. Okay, so molar mass is a 1 mole of this some elements equal to some mass. Okay, and you can see oxygen here. Here is at 15.999 gram per mole. Okay, this is 1 mole of the oxygen atoms has a 15.999 gram. Okay, but usually when I do the calculation for this one, I won't keep those 3 decimal. I usually just put 12 gram. Okay, so that's pretty close enough. For the oxygen, usually I just round it up to 16, okay? But for some of the elements, like a boron here is a 10.81. I usually just keep 10.81. I want to round it up to 11 because this is not that close to like carbon, right? Carbon is 12.011. So generally I can cut the decimals, okay, to keep the 12. But for the boron, you cannot round up. Nitrogen, you can round it to 14. That's totally fine. Hydrogen, you can round it to 1. That's totally fine. Lithium, that's 7. Okay. For the sodium, you can write like a 23. That is fine. But for the magnesium, you cannot make like a 24. Okay, because this is 24.3 something. Okay, so this is usually how I do. For the copper, you should keep like a 63.55. Okay, for the chlorine, 35.45. You need to keep it. But for the sulfur, I guess you can just cut the 07 to keep 32. That's okay. Yeah. Fluorine, you can keep it as 19. I think this is also okay. Yeah. Okay, so this is talking about the molar mass. Once again, the molar mass, you can find the molar mass of all the elements in the periodic table. Okay, you can find the molar mass in the periodic table. Okay. Okay. And then the next part we're going to talk about, okay, so how to find the molar mass how to find a molar mass of a compound. Okay, how to find the molar mass of a compound. Okay, so for example, if I have a copper sulfate, and this copper sulfate has some hydride, like a 5 hydride here. Okay, this is what you're going to see. This kind of similar formula you will see in the lab. Okay, in today's lab. What does that mean? This is a compound, copper sulfate. You already see that before, right? Copper sulfate. And we have a dot. This dot is not a multiplication sign. Okay, this is not a multiplication sign. Okay, so but this dot, that means this is a water molecule. That means this dot is talking about the copper sulfate is loosely connected with loosely loosely connected. Okay, this is loosely connected, which means this copper sulfate is loosely connected with those 5 molecules. And this 5 water molecule is called a hydrate. Okay, this 4 is called hydrate. Okay, and okay, sorry. Sorry, the hydrate is talking about the whole thing. Okay, the copper sulfate with the 5 water, this called the copper sulfate hydrate. Okay, the whole thing is called the hydrate. The whole thing is called hydrate. But if we have just a copper sulfate, okay, so if we only have a copper sulfate, if we only have a copper sulfate without the 5 water, and we call this one is anhydrate. This is hydrate and this is anhydrate. Okay, yeah, hydrate and anhydrate. This one has a 5 water, this one is not. Okay, the difference is those one has waters. And just to let you know, copper sulfate, if they have a hydrate over there, then it will show this one is a blue color. This one is a blue color. But this one, this anhydrate, those are black. Oh, this is just a white color. Okay, this is just a white color. It's pretty interesting. And not just the copper sulfate has the hydrate and anhydrate. Other several other more molecules they also have, like a magnesium sulfate. They do. Okay, they have like a 7 water. This is a magnesium sulfate hydrate. Okay, and sodium sulfate. I forgot how much the water has, but they also have the hydrate over there. Okay, so there's a lot of compound can have the hydrate over there. But here I talk about this is, okay, how do we determine what is the mass for the hydrate? Okay, what is the molar mass for the copper hydrate? Okay, so generally you need to find the in the periodic table what is the molar mass for each of the molecules. Okay, for each of the elements, like a copper. Okay, in the periodic table, the copper, the molar mass is 63.55. Okay, we can find it. It's here, 63.55. Okay, sulfur we got is 32. Okay, oxygen is 16, and hydrogen is 1. Okay, so this is what we know here. And then what you're gonna do is just based on the formula, you add them everything up. Okay, the molar mass for the copper sulfate hydrate is gonna be, okay, first we have 63.55 plus 32. This is copper, this is sulfate, plus 4 time of the oxygen. Okay, this is a 4 time oxygen. Then you plus, and here we have a 5 water, so 5 time of the water, H, 2 of the hydrogen plus oxygen. Okay, so 5 times the hydrogen, 1 times 2, and plus 16. Okay, so this is the molar mass for the copper hydrate, copper sulfate hydrate. Okay, then you add them together in the calculator. Six 3.55 plus 32 plus 4 times 16 plus 5 times 18. Okay, so the molar mass for the copper sulfate hydrate is 249.55. Okay, the unit is going to be gram per mole. Okay, so this is a molar mass for copper sulfate hydrate. Okay, and then, so what is the molar mass? What is the molar mass for the copper sulfate? Okay, for the copper sulfate, once again, for the copper sulfate, then that's just the copper plus sulfate plus 4 times oxygen. Okay, and that's it. So 63.55 plus 32 plus 4 times oxygen. Oxygen is 16. Okay, then you add them together. 63.55 plus 32 plus 4 times 16. And so 159.55 gram per mole. Don't forget the gram per mole, okay? It's talking about the 1 mole of the copper sulfate has that much of the mass, okay? So then if you want to get, okay, another, let's see, potassium SCN, okay? Potassium, this is a potassium thiocyanate, okay? Potassium thiocyanate, okay? The molar mass of this is just equal to potassium plus sulfate plus copper plus nitrogen, okay? Potassium is 39, okay? You can just write as 39. That's going to be 39 plus 32 plus 12 plus 14, okay? 39 plus 32 plus 12 plus 14. And that's going to be 97 gram per mole. Okay, this is molar mass of this. Okay, and there's one more. Okay, so what if we have a polyatomic ion? Okay, this one gonna be hard. So how about this one? Ammonium phosphate. Okay, ammonium phosphate. Once again, your do is the same thing, right? So first, we have 3 of the ammonia. So 3 times of the nitrogen plus 4 times of the hydrogen, okay? And this part is ammonia, okay? Then you're plus the phosphate plus 4 times oxygen, and that's it. So here you have 3 times nitrogen is 14 plus 4 times 1 is hydrogen plus the phosphate, the phosphorus P is 30, you can write like 31, okay? So 31 plus 4 plus 16, okay? And then you put everything into the calculator. 3 times parenthesis 14 plus 4 plus 31 plus 4 times 16. That's give us 149 gram per mole, okay? This is 1 mole of the ammonium phosphate is equal to 149 gram. Okay, so this is how we determine the molar mass of the chemical compound. How we determine the molar mass of the chemical compound. Okay. How we determine the molar mass of the chemical compound. Okay, so the next part we're going to talk about. Okay, so now generally we can so now if we have mass, we can convert to the molar mass. We can convert the mole. Okay, there's the connection between the mass and the molar mass. Okay, the connection here is the molar mass. Okay, as long as we know the molar mass, we can convert the mass to the mole, or we can convert the mole to the mass. Okay, we can convert the mass to the mole, or we can convert the mole to the mass. How? Okay, so this is a kind of like a conversion factor. Molar mass is a conversion factor. For example, you see, we know, just like what we did here, okay? For example, if we have 2.5 mole of the ammonia phosphate, we know the molar mass is 149 gram per mole, okay? So if what we want to convert the 2.5 mole of the ammonia phosphate to the mass, how do we do this, okay? So first, you write down what you have. First, we make a really long fraction, and you write down what we have. We have a 2.5 mole of the ammonia phosphate, right? This is ammonium phosphate, okay? So we would like to cancel the mole of the ammonium phosphate, and we got a gram, right? So based on the molar mass, we actually 1 mole has equal to 1 mole of the ammonium phosphate have 149 gram, okay? 1 mole of the ammonium phosphate has 149 gram. So based on this, you can cancel mole and mole are canceled, and you can use the 2.5 times 149. Then you got the mass of the ammonia phosphate. Okay, so you time 2.5, and we got 372.5 grams. Okay, 372.5 gram. And once again, it's not done yet because we need to keep the right sig fig. The beginning is 2.5, which is 2 sig fig. So you're going to keep 2 sig fig. So the right answer is 370 gram. Okay, 370 gram. Okay, so this is how we convert from mass to mole. You're using the molar mass. Once again, if you're want to convert the mole to the mass, you do the same thing. Okay, you're still using the molar mass to convert it. Okay, you still sorry, we here we talk about it from mole to mass, but if you have a mass to mole, you do the same thing. For example, if we have like a 1,000 gram, okay, if we have 1,000 gram, 1,000 point gram of the ammonium phosphate. Okay, so what is the mole of the ammonium phosphate for this one? Okay, once again, you make a long fraction here and write down what you have. What I have is 1,000 gram, 1,000 point gram ammonium phosphate. And you want to convert it to mole, which means I need to put the gram in the bottom or put the mole on the top, right? So we know 1 mole of the ammonium phosphate has a 149 gram, okay? So then you know it's 1,000 divided by 149, okay? So 1,000 divided by 149. 149, okay? Then what you have is 6.711 mole, okay? 6.711 mole, okay? And this one, at the beginning, 1,000 dot, they have a 4 sig fig, so we keep the 4 sig fig here, okay? And then 6.711, that's the final answer. Okay, so based on the molar mass, you generally can figure out, okay, you can make a connection between the mass and the mole. Okay, based on the molar mass, you can make a connection between mass and the mole. Any questions so far? So any questions so far? No? Okay, so let's have a break and then we will talk more. Today we're going to do the composition, okay, percent composition lab. Okay, everyone, please come back. Okay, everyone, please come back. Okay, so now we're talking about the relationship between the mass and the mole. Okay, we can use the molar mass as the conversion factor. Okay, so we can use the molar mass to make a conversion factor between the mass and the mole. Actually, there's another connection. Okay, there's another connection. Is between mole to the number of molecule, the number of molecule or atoms. Okay, yeah, and we do have a conversion factor here. Okay, so generally it's talking about one more. Okay, it doesn't matter is 1 mole of anything. Okay, 1 mole of certain, 1 mole is equal to, okay, 6.02 times 10 to the 23rd. Okay, here we can write it as a molecule or atom, So what that mean, molecule or atom? That means if this is 1 more is a compound, then that's a molecule. If this 1 more is an element, or then that's just an atom, right? So it doesn't matter what kind of stuff, okay? As long as it's 1 more, then that's this number, okay? 6.02 times 10 to the 23. Okay, so then what can we do here? That means if I know we have, once again, if I have a 2.5 mole of the ammonia phosphate, okay, then how many molecules are there? Okay, so what are you gonna do? You put 2.5 mole of there and you make a long fraction. So we want to cancel the mole to get the number of the molecule, right? So we put the mole in the bottom and put the molecules on the top. So based on this conversion factor, 1 mole of this has a 6.02 times 10 to the 23rd molecules. Okay, so then what is that? That's gonna be 2.5 times those. Okay, so 2.5 times 6.02 and the time 10 to the 23rd. Whoa, that's really big one. Okay. Okay, that's gonna be 1.505 times 10 to the 24 molecules. Okay, but here at the beginning we have a 2 sig fig, then we keep 2 sig fig here. So that's going to be 1.5 times 10 to the 24 molecules. Okay, so here the conversion factor is 1 more equal to 6.02 times 10 to the 23 molecules or atoms. Okay, again here we convert from mole to molecule. We can do the same thing from molecules to mole. Okay, from molecules to mole. Let's say if I have 3.3 times 10 to the 3.30 times 10 to the 25 times 10 to the 25 molecules. Okay, once again, molecule is not a mole. Okay, mole is not different like a molecule. This is a molecule, is a small number. Okay, if we have 3.30 times 10 to the 25th molecules of ammonia, phosphate. Okay, so what is the mole of this? Okay, what is the mole of this? Some people write the mole like MOL. Some people write like MOLE. Okay, I usually just stick with MOL. Okay, the mole can be write like MOL or MOLE. Okay, but I'm stick with the MOL. So what are you gonna do? Once again, you write a long fraction and you write what you have. Okay, what you have is a 3.30 times 10 to the 25th molecule. And then you want to cancel the molecule and got the mole. Based on the conversion factor, 1 mole has a 6.02 times 10 to the 23. Okay, and then you just figure out, use the big number divided by another big number. Okay, 3.30 times 10 to the 25th divided by 6 divided by here. Okay, so when you put this number into the calculator, make sure you're gonna have a parenthesis. Otherwise, it do have a question, do have a problem. Okay, make sure you're gonna have a parenthesis here. 6.02 times 10 to the 23. So the answer is give me is a 54.82. Okay, 82 mole. Okay, because the molecule and the molecule is being cancelled. What's the left over is a mole. And once again, at the beginning, I have a 3 sig fig. This is 3 sig fig. So I'm also going to keep 3 sig fig. 1, 2, 3. So the final answer is a 54.8 mole. Okay, yeah. So this is the connection between the mole and molecules. Okay, mole and the molecules or atoms. Okay, and here, okay. So any questions so far? Okay, do you have any question? Pretty straightforward, right? This is just a calculation. Okay, then if we want to, okay, so here now we have a connection between mass to mole, then to molecule, okay, or atoms. Okay, so this is a connection, right? And between mass and mole, that's a molar mass. Between mole to molecule, and that is the between mole to molecule, that is the 6 point Avogadro number. Okay, so based on this, you can generally also calculate from mass to molecule, right? Or you can also to calculate from molecule to mass based on the two conversion factors, right? So that's the same thing. Let's do just one more thing, okay? So if we have, I don't know, I just make up, okay? If I have like a 5.22 gram of the ammonia phosphate, Okay, so today let's just stick with the ammonium phosphate. Okay, ammonium phosphate. That was what is the number of molecules? So what is the number of molecules? So once again, just based on the stick with the path, this path, okay? This path is pretty clear. You need to do two steps. The first, you convert the mass to the mole. Then you convert the mole to the molecule. So the first conversion factor is the molar mass. The second one is Avogadro number, 6.02 times 10 to the 23rd. So what you need to do is, once again, you make a really big long fraction. So you put a 5.22 gram here, okay? So then you want to cancel the gram, you got a mole, okay? You want to cancel the gram, you got a mole. So here, 1 mole equal to 1 mole of the ammonium phosphate equal to 149 gram of the ammonium phosphate. Just double check, okay? Make sure I got it right. It's 149, okay? So it is 149. Okay, so now gram and gram canceled. Now you got a mole. You got a mole. So after this step, you got a mole of the ammonium phosphate, and then you want to get the molecule of the ammonium phosphate. So you cancel the mole. You put the molecule on the top. Once again, the unit on the top is always the unit you want. Okay, the unit on the top is always the unit you want. So here, 1 mole of the molecule, or 1 mole of the, doesn't matter, 1 mole is equal to 6.02 times 10 to the 23 molecules, okay? The mole and the mole canceled. So in this case, what you get is 5.22 times 6.02 times 23rd divided by 149, okay? So just a 5.22 times 6.02 times 10 to the 23 divided by 149. Okay, so what I have, 2.109 times 10 to the 22, okay, molecules. Once again, this one is a 3 sig fig. So I'm also going to keep 3 sig fig, 1, 2, and 3. So 9 can round it up. The final answer is going to be 2.11 times 10 to the 22 molecules. Okay, yeah. So it's not hard, right? It's pretty straightforward. Just based on the conversion factor, you can figure out. You can just go from mass to molecule, from molecule to mass. That's the same thing, okay? As long as you stick with the molar mass, stick with the conversion factor, and make it like that, okay? Then you can easily to figure out how to convert the molecule to mole, mole to the mass, or mass to mole, and mole to the molecule. Okay, that's the same thing. Okay, so you can based on this to figure out.